Alright, welcome to a new set of slides. This one is two weird combinations of ideas. We're going to start with exceptions and then get into what's called functional programming. I'm very excited about both of these. So yeah, let's start with exceptions. This is the one I'm going to test you on. Functional programming is just extra. I wanted to show it to you, but I will not test you on that one. But exceptions for sure, very important. So let's get to those. Fun memes about exceptions. So here is an idea. Exceptions are a new kind of C++ feature that we have not used yet. It's one of the last ones that we have not used, and I'm going to try to motivate why we need it. Alright, so here's a silly idea. Let's pretend that we're writing a division function. Probably you should just use the slash, but let's just pretend we're writing a division function, and we'd really not like to have a runtime error if the user tries to call us with a bad 0 as the divisor, right? Try to divide by 0. So this is what our function would look like. Int divide. For some reason we want this, and that's supposed to be an E. And we take the, it's called the thing on the top of your division is called the dividend, right? It's the thing being divided. Int dividend. And I am not doing well at writing today, sorry. Dividend, and then the thing you're dividing by, the thing doing the division is the divisor. And the body of this, as you might expect, would be something like return dividend over divisor. And this will crash the program if you get a bad divisor, won't it? So that's unfortunate. Let's go make that. That is sad. Okay, it has some potential issues. Does it not? I'll call it division.cpp. I'm spelling that right, yes? Yes. So here we go. Int divide, dividend, divisor, return dividend over divisor. There. Okay, so you know what's going to happen if I say this. If I make int n1 is 42, and then we'll ask the user for n2. And then we'll get it from him. And then we'll say see out the result of dividing n1 by n2. So think of how you would solve this problem. If I type a divisor that's 2, that's normal and it works. If I type a divisor 0, though, it will get a runtime error, and that's no fun. We'd like to prevent that, okay? So we'd also like to just tell the user, shout at them, yell at them if they did something silly. How can we fix it? Honestly, we're going to have to, we have to control whether we run this line, so we need an if statement, for sure in here, yeah? We for sure need an if statement that controls whether or not we run this line based on the divisor, yes? So that is forced upon us, no matter what. But I guess we can see out, we can yell at the user whenever they give us a bad divisor, but we still have to return something, don't we? We still have to return an int that somebody expected to be the answer. And that's not good, is it? Because when you divide by 0, you should yell at the user, and then there is no answer. Do you see the problem? So we are kind of forced right now to use a bunch of if statements, and even that doesn't fully solve the issue. Use a bunch. Wouldn't it be nice if there was a better way? Use a bunch of if statements. And so we could do something like this. We'd be like, if divisor is equal to 0, then yell at the user. But we still have to return an int. So what do we return now? -1, we could return some weird looking value, but then suddenly we're not sure if we got that value normally or not. You see that? That's unfortunate. So, I mean, here's about as good as we can do right now. So if divisor is 0, then yell at the user, bad divisor. But I mean, the show must go on. We're trying to not stop the program right now. So we still have to return an int and not let this line run. So we'll return -1 maybe? But then what if somebody called divide with 42 and negative 42. Now suddenly we're not sure if this negative 1 meant error or if it meant like that's your answer. Keep going. You see the problem there? So you've kind of given up an answer because of this. Just trying to check for the issue. So, I mean, that's all we get right now. That's all as good as we can do, pretty much. But at least now we'll see in the output the problem. It's like enter divisor 0, negative 1, but it prints bad divisor. Somebody should go looking. But if the program needs to continue and run forever, like, we don't know if the negative 1 meant error or that meant answer. Do you see the problem? So, yeah, that's kind of what you're forced to do because this is forced to return an int. Okay, we have no way around that right now. The way around that is exceptions. When this happens, we do not want to return any int. We don't have an answer at all. Does that make sense? We'd like to kind of skip over the return process. And exceptions are a C++ feature that lets you do that. It lets you skip out of a bunch of functions, potentially, to get to somewhere to handle an error. All right, so yeah, our job is we want to handle the error in some way. And right now we can just use a bunch of if statements, and it's still not the best. So an exception is a new piece of C++ syntax that like controls issues. You've signaled that an issue occurred by we throw an exception. Okay, that's the metaphor. It's kind of neat, and yeah, it's called an exception because it means that something exceptional has happened, and you need to take over and figure it out, handle the problem. So yeah, the metaphor is every exception is something that's being thrown. It's being thrown out into your program. It's like a ball, something like that. That's your exception. And it's being thrown. And if you do not catch it, it will stop your program with a runtime error. Okay? To handle an exception, to deal with it, you have to have a glove in your program. You have to make a virtual glove to catch the exception. Okay? That's the metaphor. So an exception gets thrown by someone when they notice that an error occurred and they don't have a real value to give back right now. They throw an exception, and let's just use the present tense, and it's your job somewhere in the program to catch it. Otherwise it's going to hit things, and if you don't handle the error, it's going to like break the glass of your program and stop it with a runtime error. If you forget to catch exceptions that are thrown, then it results in a runtime error. Okay, that just means you didn't know how to handle it at the time. So that's the idea, and so let me show that to you. Let's see the new syntax involved. All right, so you've technically already seen exceptions actually. So like vectors, if you try to go to a weird place in a vector, like let's say this is a vector, 4, 5, 6 at indices 0, 1, 2. If you ever tried to go to a vector with the .at, right, index 3, let's say, if you try to go here, it doesn't exist, and it will throw an exception. It's called the out of range exception. All right, so that's kind of neat. That's something that we've already dealt with technically. It's just that we didn't know the problem. It turned into a runtime error because we did not handle the issue, but it threw an exception secretly. Okay, so let me first prove that to you. Containers, vector. So if you say .at on a vector, where is that? So .at, it will throwing an out of range exception if it's not a valid element. That's kind of nice. All right, that's very helpful for us, and so let's see that in action. I'll call this try catch because that's going to be the new syntax. So I need vectors. I'll make this exact vector 4, 5, 6. And yeah, let's go to v at 3, which does not exist. So if I run this, it's going to stop with a runtime error. It's like terminate called after throwing an instance of out of range. Do you see it? And like here's some extra information. So an exception just got thrown. It's called an out of range exception, and it caused our program to stop because we did not handle it. So C++ just thought that like we weren't expecting that. So I don't know what to do. I'm going to stop the program right now. All right. that is the idea of exceptions, and we can handle this exception and keep the program running if we want to. All right. So first of all, out of range is just an object. It's just a type that you could make an object out of. So out of range is just a random type that has some information inside of it, about the error that happened. So I'll talk about that in a second. But it's just a type that gets thrown. So you could have thrown an int. You could have thrown a vector if you wanted to. It's just a value. This is just a special exception type. But you could have thrown anything. So every exception that gets thrown is just a value of some type. So you could throw an int, you could throw a string, but usually you make your own exception type out of range. All right. So yeah, let's catch the out of range exception and handle it and not let the program end. So to do that, we use what's called a try catch block. All right. You say try, and then in between curly braces, you put code that might throw an exception. It's like, please try to run this code for me. All right. It attempts to run that code, and then any exceptions that occur, they jump to a corresponding catch block. All right. So here in the try, you put any code that might throw an exception that you know how to handle. It doesn't have to throw an exception, it just might. Code that might throw an exception. All goes in the body of the try. And then, based on the kinds of things that make it thrown, you have one or more catch blocks after the try. All right, and here's what it looks like. You say catch, it's kind of like a function almost. And then in between parentheses, you put the type as if it were like a parameter. It's the type of thing that's being thrown, potentially, like one kind of the things, one potential exception type. It's like out of range. And customarily, you catch your exceptions by reference. And then you give it a name. It's like here it is. It will be able to hold on to that out of range exception. And then you put curly braces and you say how to use. All right, if an out of range got thrown, it's going to stop the code. Maybe it got thrown up there. It's going to jump straight to the corresponding catch for that particular type, out of range. And then it comes down here, and you can use E inside this body. And this is where you handle the out of range exception. Okay, so yeah, let me show that to you. And if there were other kinds of exceptions that could be thrown, you would have more catch blocks down here. You'd say catch again. You start chaining them. Catch some other type, maybe an int. You can have it as many as you need. And let me draw that in a different color, maybe. All right, let's catch an int. You start chaining them like else ifs. Int I. All right, maybe if an int gets thrown, now I know how to handle it. I'll run the code in here. All right, so that's the setup. You can have as many catches as you need, but we just need the one. So we'll turn this into a try catch now. So try to do this. If an exception occurs, and it's gonna, right? Then let's catch the ones that we understand and know how to handle. So we'll catch an out of range. You catch it by reference, call it something, call it E, and then what will happen is the second the exception occurs, which is during the dot at, the vector library is oh, that's a bad index, I'm throwing an out of range exception. It will jump to the catch and start running this code immediately. So C++ jumps here if an out of range exception occurs in the try block. All right, so our job now is to just handle the exception in some way. Maybe we ask the user for another index to go to, something like that. But I'll just be silly and lazy. I'll just type, uh-oh, problem happened. Every out of range object, though, called E, is the one we're taking right now. Every out of range, it has something inside of it. It has information about the kind of exception that occurred. It inherits from this base type called exception, and so here's its constructor. It's taking when somebody the vector library builds an out of range exception, they're giving it a string that describes the problem just as words, and so we can go in and get that string with it's a cute operation. It's called the .what member function. All right, so there's a .what member function that describes, it gives you back a C string as to describe what went wrong which is hilarious. I love that name. It's called dot what. Like, what's the problem here? So you can ask your out of range exception what the problem was. There we go. By calling dot what. E dot what. Tell me the problem, please. And so we got to here. The exception occurred. It jumped straight to here and ran all this code. And that was the end of the whole try catch. So, e dot what, the string inside was like information about the problem. Like, oh, index was 3, but the size is 3. That was too big then. Could only go up to size -1. Okay, so there's that one. What else do I want to say? So the next thing, I guess, is that when an exception occurs, it stops the try. It does not come back to the try. So like be at 2. If you have another line after this, this line will never get run. This line will never run. Okay? It will never come back. C++ just thinks that all bets are off the second that an issue occurs. So it tries this, it finds that an exception occurs, it throws out of range, we catch it, we handle it, and that's the end of the whole try catch. Okay? We're never coming back to here. Never, ever, ever. Okay? So that's the idea. It's going to stop at the first exception. Okay? You handle it. Like if you wanted to come back to this line, maybe you'll have to like do this in a loop or something. Like you'll have to put the body again somehow. So maybe that's a reason to have short try bodies. But I think that's what I wanted to say here. So you can also throw your own exceptions. It's the library here, the .at method's implementation was noticing the problem. It did not know how to handle the problem, but it just alerted us by throwing an exception. If we're making like a library, we can also throw exceptions when we notice things that went wrong, and then that just lets the user catch them eventually and handle them when they know how. Okay, so yeah, you can throw whatever you want. There's different kinds of exception types. There's a fun one, a useful one. It's called runtime error. All the standard libraries exceptions live in this header called standard except. So like here's a bunch of predefined exception types. Runtime error is a good one. Just like out of range, it takes a string that describes what went wrong, and like you can call the .what on it too. It's perfect. So you can use that for sure. Runtime error takes a string and returns that string when you call .what. But you can throw anything. You can throw any type, not just stuff from that header. So you could legitimately just throw an int if you want to. And here's the syntax for it. You say throw. That's the new syntax. To throw an exception, to alert somebody, like to throw the ball out into the stands. You just say throw, and then you give the value you're trying to throw as an exception. You just say throw 42. That throws in it. That's fine. You could throw a double, any type, 3.14. But usually you make your own or use like a standard except type. But yeah, let's see that. Let's see that in action. So we'll write some functions that throw different kinds of things, like a throw string, a throw int, and a throw runtime error function. I think that will be useful. So let's see those. And so you're going to throw exceptions when you notice an error. You don't know when you notice the error usually how to handle it, and throwing an exception is you handing off the problem to somebody else. Okay. So let's see. I'll make a new file. I'll call it throw.cpp. And so, oh man, I need a bunch of stuff. I need strings. I need standard except, and that should be enough for now. So here's that. Let's make a couple functions. We'll have a throw string function. It'll just be void. This is just the function that throws a string. So string s equals blah throw s. All right. And then I'll make a function that throws an int. Throw 42, and then I'll make a function that throws a runtime error. And so you can build a runtime error object like this, runtime error, and then in its constructor it takes a string that describes the error. We'll just put something dumb, so that'll work, and then we'll throw that. Normally you're supposed to, like, in an if statement, when you notice the problem, actually do this, but we're just being lazy here, okay? So there's that one, and let's see what else. Well, let's make a function that randomly calls one of these that throws like a string or an int or a runtime error. All right, so here's my silly idea. I'll be like, I'll make a function called doStuff. Oops. doStuff. And then inside of doStuff, it will either call like runtime error, string, or int. Okay, and so let's do that randomly. So I'll use cstdlib and ctime, right? srand time 0. And now I can randomly do something. So I'll pick a number. Choice is rand mod 3. So it'll be either 0, 1, or 2 randomly. So if choice is 0, let's throw an int, throw the int function. Otherwise, if choice is 1, I'll call throw string. That'll throw a string. And then otherwise, that means choice must have been 2, I'll throw the runtime error. Bam, just like that. Alright, so that's kind of funny what's happening here, but I hope you see it working. So I've got a bunch of functions that throw something, and here I am in do stuff, picking randomly one of those. So I'm not sure which one's going to be thrown when I run my program. It's like one of those will get thrown when I call do stuff. Oops. Let's see, what do I want to say before I write code anything? No, I think that's good enough for now. So here. Let's compile and run this. And I'm not catching anything right now, so it's just going to be like, oh, an int got thrown randomly, like we hit here, and then like it stopped the program because we never caught that int. And this time it threw an int again. This time it threw a string, but we never caught it, so we're just kind of stuck. And there's the runtime error. If it's one of the standard libraries exception types, it will call what for you, which is kind of nice of it. But again, that turns into a runtime error if we don't handle it. So let's handle it. Okay, so let's see. Let's do it in main. So to handle an exception that gets thrown, we have a try catch. So do stuff might throw an exception, and let's say that main is the place where I understand like how to handle all the potential exceptions that might happen here. So I'll do try catch here. So I'll say try, and then you give as many catch blocks as you need. You say catch, and then you start saying all the different kinds of errors, exceptions that you understand and know how to handle should one of those get thrown in this code. So catch a runtime error might get thrown, catch it by reference always, and like the second you have a catch block, it'll jump here if a runtime error got thrown. And that's kind of like you shouting out to the world, hey C++, I know how to handle a runtime error exception. That's what's going on. Okay, so just for fun, let's see out. Like we caught one here, caught a runtime error in main. And then what's information about it? We're calling it E right now, so we can output e.what, describe yourself, and that'll work. That can be how we handle the error. Okay, but then you have as many catches as you need for other stuff. So let's say we could also throw an int, right? Ints and strings. So let's catch those. Catch a string by reference. This is again you shouting out to C++ that you know how to handle not a runtime error, but if a string gets thrown now. That's you saying, I know how to deal with that. Come to me. All right, so caught a string in main. We called it S. And then likewise, if you need to catch an int, that's one more. Catch it by reference. And so yeah, just like depending on the one that actually gets thrown, you'll jump to the right catch block. So this is us claiming that we know how to handle an int exception. Caught an int in main, and it was I. Okay? I hope that makes a little bit of sense. And yeah, that's the secret. So that's do stuff in a nutshell. Is going to throw some of these, one exception only, right? It's either string int or runtime error. And so that's happening. And down in main is where we're handling the problem. It's far away from the do stuff, far away from the throw. Like the throw is happening in one of these functions. Like we're hitting here and somehow jumping, teleporting all the way down to main. That is the beauty of exceptions. It lets us go to weird, faraway places because that's where we know how to handle the things. So now we're happy. Now it's like, all right, a string got thrown, so we jumped right to here, caught a string in main. Boop. This one was a runtime error, so we jumped to here, handled the runtime error, printed the what. and then eventually it will be an int as well. There's the int. So it jumped to here inside of do stuff. It was really this line right here, right, that threw the 42. And that was called from here. So like we're unwinding the stack all the way down back to main, and that's where we're handling the exception. And yeah, that ends the entire try catch. All right, so this is the second that's done. The whole point of doing this is so that you can continue your program, like you have the rest of your program down here. We have not stopped with the runtime error now. That was the goal, and we have achieved that goal. Okay. So yeah, now we're back down to the rest of the program. Also remember that, like I was saying before, the try block is going to stop the second you get your first exception. It does not come back. So if I have 2 do stuff calls, we're never going to get to the second one. Never, ever, ever. Because the very first time, do stuff is guaranteed to throw, right? Do stuff is guaranteed to throw an exception. And so we're going to catch whatever exception got thrown. It was the string. So like the string got thrown from this call. We jump to here, we catch our string, and that's the end of the entire try catch, right? It does not come back and redo stuff. Okay? I hope that makes sense. So that's the secret. That is important to understand. Yeah, you usually want to keep your try blocks short because just think about it. If you have a bunch of things, a bunch of different function calls like f and g, they all might throw different kinds of exceptions, like maybe f throws a double, g throws a bool. You'll have to add a million different catch blocks. So it's good practice to just like have short tries, because otherwise you'll have to do a lot of different kinds of recovery options. So yeah, and then you'll need a ton of catch blocks. So just keep that in mind. Keep things short if you can. Yeah, I think I wanted to say that for now. And you could catch exceptions anywhere, right? Like the second they get thrown, you can catch them. It does not make sense to do a try catch in these functions. I hope you see that, because like, what's the point? You could have used an if statement if you just wanted to stay in the same function and handle the problem. Does that make sense? That's very, very important, and I want that to make sense. It's like, there's no need to catch in the same function as you threw, because you could have just used an if statement. The whole point of throwing exceptions is to be able to handle them far, far away from where they got thrown. All right? I hope that makes sense. All right, so it does not make sense to add try catches here, but we could have added try catches and do stuff. That's farther away. So let's do that actually. So let's say it's these lines right here that might throw an exception. So let's add a second try catch. Try to do all these things. An exception will definitely occur. And let's say that let's pretend we don't have enough context to catch maybe an int. Like if an int gets thrown, I don't know how to handle it and do stuff. But if a string or a runtime error gets thrown, let's say that I do know how to handle those in do stuff. So I'll add catch blocks for those. Runtime error and for strings, but not for ints. All right, I have a reason for this. And that's usually going to end up being the case. Like I know how to handle some of the things up here, and then some of the things I have to wait. I only have the context way down here, and I can only handle them then. So let's add a runtime error catch block and a string catch block. And this is now in do stuff. Call it a string in do stuff. Okay? So this is us claiming to the world that we know how to handle a runtime error in do stuff. We know how to handle a string in do stuff. Does that make sense? We have 2 different places to catch runtime errors and strings now. I hope you see that. So, interesting. What do you think is going to happen when we run this program? Boop. It looks like a string got thrown, and so let's think about this. So do stuff was called, a string got thrown, but we try catched, and we had the ability to catch a string up here, and so it did it. It handled the issue, and do stuff ended normally because of that. So we caught the string in do stuff, and this ends the try catch, and now do stuff actually returns finally. Does that make sense? It's going to go, the string exception got handled by the closest catch block. That's very important. All right, so it's going to the closest one, and that means do stuff returned, and actually we could have more down here now to do more, to do extra stuff, because this line will actually get run sometimes now. So I'll get here if the error gets caught in do stuff, because do stuff is handling some things now. If it was a string or a runtime error, do stuff was going to end normally now, from our perspective here in main. Does that make sense? Let's recompile. Let me try to talk about it. Int is the only one that will get down to main again though. So like if in do stuff we called throw int, we try catch, and we did not have a way of catching ints here, so it just keeps on unwinding until it finds a catch block that handles that int, and so it went to main. All right, so it did not run this line. But if I rerun it, because it's random, look, so this one it threw a string. So we're here in do stuff through a string. So it got to here, but we were try catching, and here was the closer string catch block, and so it got to this code. And so it caught the string in do stuff, which means that ends this try catch, and we hit this closing curly brace finally for do stuff, and do stuff returns normally from main's perspective. And so this line from main's perspective did not throw an exception. All right, and so the rest of the code in the try block gets run then. You see that? That's pretty cool. Same for runtime error. It's randomly not doing that very easily. So yeah, runtime error, we're also claiming that we know how to handle that. It's closer up here, so we'll handle it at the closest spot that knows how. So we'll get to that one. And again, from main's perspective, do stuff did not throw anything, and so we run that second line. But if there's an int, like these, it's going straight to the int handler, because like that's the only place we know how to handle the int. It's going to unwind until we get to there. Okay? I think that's pretty cool. I hope that is making a little bit of sense. It's a new idea, though. It's going to take a while to sink in. But yeah, it's going to go to the closest one. And so let me draw a picture for you. Okay? So there's kind of a concept of a second stack now. There's an exception handler stack when things happen. All right? So yeah, let's talk about this. So like I was saying, exceptions are super, super nice because they let us catch anywhere. So they can be caught, we can catch our exceptions far, far away from where they got thrown. It's like this int, for example. It's like inside of do stuff, inside of throw int was where the throw actually happened, and we just started unwinding, chopping ourselves off the stack until we got to here. That's pretty neat. Okay, so yeah, you can do that. And the way that C++ knows where your exception handlers are is it builds up a little chain of them. There's like a chain of exception handlers, a chain of catch blocks that it understands are being hooked in right now, that it knows to go to if an error happens. And it's going to store a stack of them because it needs also, because maybe there's like 2 ways to catch an int, it's going to go to the closest one because it assumes that's the place that has the most context and knows how to handle the problem the best. All right? C++ will go to the closest one for the given type of thing that just got thrown. Okay, and let me draw that for you now. So yeah, just like for function calls, C++ keeps track of like a stack of try catch blocks that we're in. It knows how to handle things. So yeah, let's talk about this. So let's say let's do this. So we're in main. We call this c.random number generator, and then we hit the try catch. All right, so we're about to run do stuff. So here we're in main. We're about to run do stuff. Let me draw what I mean here. About to call do stuff. But before we do, we're in a try catch block, and so we're claiming that we know how to handle a runtime error, a string, and an int right now. Okay, so that's going somewhere. C++ is saving that information on an exception handler stack. That's how I want you to think of it. Exception handler stack. And so it's saving like all the catch blocks that it knows about right now. And so we have a few. It's like main is claiming to know how to handle a runtime error right now, and so like we'll save that fact. If we ever need to go handle a runtime error, we can go there now. We know that. Main can handle a runtime error. It also is saying I know how to handle a string, so main also knows how to handle a string. We'll save that just in case we need to go to that catch block. Main has a string catch block, and then finally main has an int catch block. Okay, and then so that's saving that information, and then we're about to call do stuff. So now we go into do stuff. So do stuff does its thing, it does this, and then so yeah, let's draw that fact on the stack. So main calls do stuff, and now do stuff's running. It's doing its thing, and it also has a try catch. So we're going to get to the body of this try, and so if we start running this try, we have to save the handlers. So like, all right, inside of this code now, which I am now trying to run, I know how to handle a runtime error and a string. So that's saying do stuff. Right now we're in the do stuff function for those try catches. So this is, we have to save now on our handler stack that, okay, do stuff now knows how to do some things. It knows how to handle a runtime error, and it's also claiming that it knows how to handle a string in do stuff if one ever gets thrown. So yeah, that's the exception handler stack, and this is just the main normal function call stack. And let's say that just randomly we picked 2 and throw runtime error was the function that got called right now. So now we're here in throw runtime error. So just for completeness' sake, we're calling throw runtime error now. Oops. Oops. Why can I not draw suddenly? There's a problem. There we go. Through runtime error. All right, and then we hit this line, throw that runtime error. It gets thrown right there. Okay. The second that happens, what C++ does is it starts looking here on the exception handler stack. It's like, all right, a runtime error just got thrown. That's the thing that just got thrown right now. And so it's going to look at that handler stack from the top down, and it's going to go to the first one that matches the type of thing that just got thrown. All right, so it's like, all right, string. Nope, it was a runtime error. Goodbye. So you see that the next one, though, is runtime error. So this is therefore, and that was keeping track of this place right here, this catch block, yes, the one in do stuff. And this is the closest matching handler. Closest matching handler. That is important. All right. And so it goes to here and like, all right, I understand what to do. I'm going to jump to there. And then it's like, okay, because an exception just got thrown and I handled it, I'm now done with this try catch. And it changes where it was running. Because it used to be running up here. It's like this function didn't even return from C++'s perspective. It jumped straight to this catch block. Does that make sense? Then we're done with this. And then we like go back and do normal things. So like we somehow also got out of that function too. Okay, C++ was moving us around. So that's what happened. All right, I hope that makes sense. And that's kind of how it knows. Even though there was another runtime error exception handler in main that was farther away from the problem. And so C++ is always going to try to go to the closest one because it thinks that you know most, you know best up in that one. Okay, closest to the problem and where it occurred. Okay. So with all that explanation, we can now do the division example in the nice way, using exceptions in a way that actually makes sense and works. Are you ready? So yeah, instead of like returning -1, now we have a way that we don't have to return anymore. We can throw an exception. Division fixed.cpp. All right, so let's throw like a runtime error. I think that's the idea. So we'll throw a runtime error in the division function. And we can handle the exception by like asking for a new thing to divide by. So here, let's get this going. I guess honestly, I should just have stolen this entire file. So here, let's do most of that. So I will take all these there. All right. So here is the bad stuff. Let's fix this now. So if the divisor was 0, instead of couting and like returning some special value that we have to like give up when we're not sure if that's a real answer anymore, the right thing to do is to throw an exception whenever we notice the error. All right, so we're going to throw a runtime error. We just build it on the fly like this. Call the constructor with the string inside. It's like division by 0. That's the string that we can put inside. And this is what the divide function turns into. So it's going to throw the runtime error if an error occurs. And notice that we don't have to like return an int or anything. Like if we get an int back from this function, we know that it ran correctly. We got to here, and that was the real answer. That's perfect. That's what we wanted. Okay. Again, you should not have a catch block up here. There's no need for a catch block in the same function as you threw, because you could have just like, all right, if I want to handle it right now, like you could have just handled it. Does that make sense? The whole point of exceptions is that you can handle the error far away from where you notice it. Okay? So you could have just started adding more lines to handle it if you knew how to handle it up here. But the job of the divide function is just to notice the problem. We're not sure what the user was trying to do here and why they were dividing by 0. We cannot like try to fix it for them because we don't know enough. Let the user handle it. Here we are noticing the error. Let the user catch it and handle it in the spot where they know how. All right. So main is a good place to handle this error. So like, all right, it's this line that's going to cause the exception. Yeah. So let's just, I don't know, let's put all these things in a try catch. Here's how I want to handle this. So I will do this, right? This is code that, like, these will never throw an exception, but this one might. And so if it does, I will catch it, runtime error, reference E, because of that line right there in that if statement. So if a runtime error occurs, let's handle it. Handle the error by asking for a new divisor. It's like, that one was 0, that was bad, do it again. Try it again, user. So here's how we can handle it. We can say cout can't divide by 0, try again. And then we want to ask them again for a new number. And so we kind of want to come back to this code. So we'll put in a loop. While true, infinite loop. Watch what we can do here. Due to the way that try catches run, if an exception gets thrown on this line, it'll jump straight to here, and we're just going to stay in this loop forever, right? But watch where I can add a break. Do you see how perfect that is right there? Because only if an exception does not get thrown. If one gets thrown, we're jumping here, and that ends the whole try catch, and we try again, right? And we run the body again. But if no exception happens on this line, then we don't jump away, and we run the break, which breaks out of the while that we're in. You see how that's perfect? It'll keep on re-asking, rerunning this entire try catch until the user gives us something good. So hopefully that compiled, and let's try it. Yeah, in our divisor, if I do 2, it's fine because it gets to this break, right? This actually ran, we got to this line, it was happy. Here, let me split screen it too, by the way. So here we are in main. Boop, just like that. Perfect. And yeah, it's just going to keep trying though if we give a bad value. If you say 0, what happened, right? This threw the exception. We caught it in that end of the try catch, so we never got to the break, and we try again. See it trying again now? If I keep typing 0, it'll just keep on trying. It'll never break. It'll never get to this line until I give it a good value, like -42. And now this can return -1, and we know that that was the real answer. It's not an exceptional case anymore, right? We did it with exceptions, with runtime errors instead. Okay? I love it. That's how it should be. Okay? So yeah, I think for the last piece of exception stuff, I would like you to try something, please. I'd like you to have this factorial function that we were working on in the recursion slides, because there isn't a potential issue with the factorial function right now. So let's copy that in. Let's see, lecture, maybe it was 21? Yeah, factorial.cpp. Let me put it here, and do you remember this factorial problem? So factorial, this is now in the code from class if you want to go find it, or just like pause the video, type this out. Here's your factorial function. If we get 0, if we get a small value, like if we're trying to take the factorial of 0 or negative numbers, we're going to hit this recursive case and loop forever. Do you see that right now? Factorial dash o factorial. Or let's actually do that down here. So like I can get rid of this iterative factorial. And so like this one will work, but like this one will not. Does that make sense? It's just going to segfault. It's going to keep trying, keep running the function. So, because it keeps doing this, factorial of -1 times factorial of -2, -3, -4, all the way to infinity, because it will never hit the base case. So that's a problem. We should notice that and not get a segfault, because that's scary to the user. All right. So what I would like you to do is add an exceptional case to our factorial function, because right now what it's doing, if we call it with like factorial of -1 or -2, like here's the relevant code. I'll just put it on the slide maybe. Let's put it right there. Do you see how if we called it with fact of -1, it would just like keep running this recursive case, and now it's going to try calling, all right, I need to multiply my -1 by fact of -2, multiply that by fact of -3, and so on and so forth until the end of time. That's why it segfaults. So don't let that happen. Anything below 1 right now, we cannot handle it. We'll just infinite loop. So fix that. I'd like you to add a check for that, and then catch that error. All right, catch the error. Maybe ask the user for a different problem or a different number to take the factorial of. In some way, handle this issue. All right, don't let it get to this line for those problems. So give that a try. Did you get it working? So here's one way to think about it. It's just like, all right, we can do runtime errors again. And we should check, right? We have to have another if to check to make sure we don't get to this line. So like if n was less than 1, it's like it's got to be 1 or bigger to actually do things correctly. So if it was less than 1, then we have an issue. So we'll throw a runtime error. And be like, can't calculate the factorial of numbers less than 1. Something like that, sad face. And now that's perfect, because if we call it down here, we will not, at least we won't segfault right now. We'll get a runtime error, we'll get an exception, and it will print it out for us by default, but we should probably handle that problem, right? So we should try catch it. So try to run these lines, they may throw an exception. And then if they do, we can handle one. We can handle it. Catch, runtime error, do like see how e.what to handle it, however you want to. So that will fix it. That's a good thing that you should do, right? So the first one will work. The second one is just going to like, okay, up here, we hit the throw runtime error, and here we are handling it. Jump straight to here, and we deal with the problem. We don't get a scary error message now, right? So that, I think, is all that I want to say about exceptions. It's a great way of, it's returning without returning. It's a way of moving around your code to a place where you have marked that you know how to handle an issue. Okay? That's what exceptions are really good for, and that's what I wanted to talk about for those. I think the next thing that I want to talk about is a brand new topic, functional programming. So let's look at the time, and then I'm going to have to pause the video, prepare, and then I'll be right back. It will look as if no time has passed for you, though. Alright, so let's talk about functional programming. This is a new topic. First of all, I promise to not test you on it. It's a fun idea, and you'll need it one day. Functional programming is the opposite of imperative programming. So we need to talk about that term. It sounds a whole lot like iterative. Remember that word? Very similar word. It honestly has a lot to do with that, iteration. That's a key feature of imperative programming, but it is something different, so we got to talk about it. So imperative programming is it's essentially what we've been doing this whole class. It's what you learned first. It's a programming paradigm. It's a way of writing programs that uses little statements to change the state of the program over time. Okay? That's the key. So statements change a program's state over time. And yeah, so it's like, as we've been learning, it's essentially all that we've been learning. It's like we're performing tasks through a sequence of steps, and we're messing with the values of variables along the way. So like eventually things are getting like the values of variables are changing, stuff like that. That's pretty much what we know to be programming right now, isn't it? It's like, all right, I do things in order, and I'm messing with variables. Like this sum function, for example, that is like it's starting sum at 0. It's iterating, right? 0, and then when I'm summing, like I'm running this line, sum equals sum plus whatever. I can't draw an M right now. Dot dot dot. And so like the first time it runs, it'll put a 1 in there, then it'll put like a 3 in there. Dot dot dot. And like we're messing with the sums variable's value. That's normal. That's what we do. We just like run a bunch of statements, and this is affecting the state of the program, right? Sum is a variable, it's part of the program's state, and it's changing, okay? Functional programming, or FP for short, is when you don't do that. You do not change the state of the program in that way, all right? You keep it all the same, keep it all pure, okay? So in functional programming, it's what you do is to make your programs, you just make a bunch of functions, I guess, is the easiest way to explain it. Like we're making a bunch of functions now, and we're gonna run those and compose them. Like that's the basic block of building things with, okay? So yeah, in functional programming, we cannot run this line. It's x equals x plus 1, not allowed, all right? That's not okay. So we don't like the values that change. That's not okay in functional programming. It's very mathy, it's very pure. So like emphasizes the use of functions and avoids mutable data. So we're mutating the value of a variable in this kind of imperative program. We're not doing that in functional programs. So that means every variable is like a mathematical variable. In functional programs, we say const all over the place. Right? This is kind of what functional programming is all about. You say all your variables are constants, and then like you're making a bunch of little functions that you're using to build part of the answer. Like you're chaining them together. You're composing them. Okay, so that's the setup. That's what's going to go on. Okay, so let's see. How do I want to do this? This is code, right? This code right here is imperatively summing the values of a vector. I hope you see that. Imperatively summing the values of a vector. How do you do that then, if you can only use const and you can't like mess with the value of a sum variable? Well, the answer is going to be recursion. All right, recursion is everywhere in functional programming because that lets you like not mess with things. It lets you have a new stack frame for new values, for new work. Does that make sense? So yeah, let's sum up a vector using functional programming now. And so like if we say const here, we can't change the sum variable. That ruins that whole code. So we cannot use a for loop, we cannot use a while loop, we have to use recursion. All right, I'll teach you how to do this with normal recursion, then I'll show you something called tail recursion, and then there's a function in a fancy standard library in the numeric library that'll do it for you. Like C++ has some functional programming features built in. So yeah, we have to do it recursively. Recursion is a key in functional programming, and they try to make it easier. C++ is not really a language meant for functional programming, but several languages exist in the world that are meant for functional programming, and so they make it very easy to do recursion, easier than C++. But yeah, let me show this to you in C++. I'll call it sum vec fp.cbp. Oops. And so what I'd like is I need vectors. So I'll make my vector. Let's see, can I steal a lot of this code? Let's start with this, right? But we cannot do it anymore. Let's do that. And then of course this messed something up. Substitute the weird space character for a normal space character. I think it's happy now. There. So this is imperative right now, which is a no-no. So it will work, but this is what functional programming is all about. We cannot do this, we cannot update a value, so it doesn't even compile anymore. So something has to change. All right, so what we'll do is we're going to make a function. All right, we're going to need to make a function that sums up our vectors. Like a vector, I'll make a sum function that takes a vector and like gives back its sum. Like that's what we're kind of forced to do now. And this won't quite work the way I'm about to show you, but like morally this is right. Something like this, right? We want to be like int sum, take a vector, constant vector of course, vector reference v, and somehow give back the sum without looping and like changing the value of a variable. That's what we have to do right now. So the secret is going to be we can break down, right? So we can't use a loop. We can break down the vector just like we were breaking down strings recursively. Remember that? Into like the first element and then the rest of the vector. That's a thing. We can do that just like we were doing with strings, like the first character, rest of the string. We do the same thing for vectors. And that's how you can call recursively with a smaller vector, because something needs to get smaller in recursion, and that can be the vector itself. So we want to split up the vector into, first thing, index 0, and the rest of the vector. If only there was like a subster on vectors. And so kind of what we want to do is like, in the recursive case, the answer is like something like return v at 0 plus the sum of the smaller vector. Morally, that is correct for the recursive case. All right. The code does not make a lot of sense. It's hard to create that smaller vector right now. I will show you a way to do it though. So here, so that's kind of like our dream. That's what we'd like. And the easiest way to get there, to pass like the smaller vector in some way, without messing with things, is to start it and have a second argument. Here's what we'll do. So here's how I want to do this. So I would like to have a sum function that took the vector that I want to sum up, and then we'll start it with a 0. Like that's the index. That's the starting index of the vector that I want to look at right now. That's the beginning of the piece of the vector that I care about summing. Does that make sense? So we'll start with 0 because like that's the start of the whole thing. And then the smaller vector sum we can get with a recursive call like this. We can say sum, oh no. We can say sum v like 1, like treat the vector as if it's starting from 1 onwards. That's the smaller vector. And that'll call sum v2, if you add that second argument. Like you get that ability, and eventually you'll hit the base case of the empty vector. You see kind of how that would work? So that's what I want. That's how we can fix it. We just add another argument. So int cur index, and you better believe that's going to be a const. All right. So yeah, we're going to split it up into index 0 and the rest of the vector. And the way we're going to do that is like based on the current index. That's the start of the little mini sub vector that I'm considering right now to sum. So yeah, and then the base case is I'm at the end of the vector. So how do you know that you're at the end of the vector? It's like when cur index is bigger than anything in the actual vector. That's not a valid index anymore. So if cur index is way too big, then like it's supposed to mean starting there, go and take until the end of v. V's already over, so that'll be our base case. Return the sum of all the values in an empty vector. That's 0. There's nothing left. Invalid index. And then otherwise we're in the recursive case where we really can do the thing now. Sum v at 0 with the smaller vector. Return v at the start of the vector that I'm considering right now begins at cur index. And then we want to sum the smaller vector, which means add up and then call ourselves on the smaller vector, so pass along v, and it's cur index plus 1. That will compute a brand new value to go into this next argument. Does that make sense? And we're never messing with const, like we're never not using const correctly because it's a brand new int. Like give it that value and then it just never changes. That's perfect. And so this really will work. Ask me if you have any questions about it. So this has to be sum v0, that's where it starts. This will work. Again, I'm not testing you on this, so I'm going to go a little fast, but it's going to do the right thing. All right. This is recursion, doing the summing problem, using const all over the place, using a function to handle our issues. This is functional programming. All right. So that's one way to do it. But if you could imagine that if you had a size 1 million vector, your stack would blow up. You would get a runtime error. You would blow your stack so that like you get a stack overflow even though like you had a real amount of data and you weren't like infinitely looping. You just had so much that you couldn't store it on the stack. There's a better way. All right. So it's called tail recursion. All right. There's a way to not have to use the stack but also still have recursion. Surprisingly, it's very cool. Let me show that to you. So here, let me show this to you. It's what we're going to need is instead of it this way, instead of like letting this sum up the whole thing and return back the sum, we're going to change the way we iterate. Okay, we're going to change that. What we will do instead is, I think it's just easiest to show you. Again, I'm not testing you on this stuff. It's just very cool. So here's our original sum. I'm going to make a tail recursive sum. All right. So in addition to passing along the vector and like where it begins, like that, we'll also have another argument called, of course it's going to be const and accumulator. And this is going to be where we're putting our answer, all right? And the way it's going to change is that when we hit our base case, we're going to return accumulator, not 0. It's just the job is to, we're going to build up the answer in accumulator, and once we hit the base case, the answer is ready, okay? So there's nothing left. Return what we have built up. That's that. And then in the recursive case, instead of like having to make a recursive call and like wait for the answer, sum it together, and then give back something, I'm going to do this. Return a call to sum with the smaller vector, sum up the smaller vector, And then remember that v at cur index is part of my answer. It's part of the thing I'm trying to accumulate. Do you see that? So take whatever was already in accumulator and shove that there too. Does that make sense? And now it's just return a call to sum. Smaller vector. I guess we called it sum tail. Sorry, sum tail. That's it. That probably seems weird to you, but that's what's going on. All right, and let me try to walk through how it's going to run, but let me show it to you. Let me show you that it's going to work. So this is sum tail, and then we start our accumulator. It's like a value that we're summing into. Started at 0. So it's calling it a little bit weird, but again, we're going to get 15 in a different way. All right, so here's kind of what the stack looks like now. We still have the stack though. It will still blow up with a size 1 million vector. Unless we turn on a cool feature of the compiler. So here's what's happening right now. We said sum v0 and 0 for our accumulator, and then we hit the recursive case, and we notice like the thing at index 0 was a 1, so we started adding that into our vector. It's like, all right, return sum v1, and then we're accumulating 0, the original 0 plus the one that we saw in our index 1. And that's eventually holding part of the answer. We're eventually going to hold the real answer. Then that calls sum v starting from 2 onwards, and then it added the thing that it saw at the current index, which was 1 this time. It saw the 2. It added that into the accumulator variable, so now it's holding 3. And like this extra variable is holding the right answer until we hit the base case. Then it has the full sum in it. Does that make sense? And so like the final answer doesn't really depend on any of these anymore. Like there's no more work left to do. It's like whatever this thing's result is, that is my result. Does that kind of make sense? That's what tail recursion is. Okay? So like we don't even care about this original call anymore. Like this is whatever this gives back is the final answer. And then we don't care about that call either, because whatever this gives back is the final answer, all the way to the base case. And so you can turn on tail recursion optimization in G++. You can say, notice this. Notice that there's no need for these stack frames anymore. Instead, you called sum v00 first, and then that's going to return the result of sum v11, and there's no work left to do after that. Just replace the stack frame with that. All right, call sum v1111. That's my answer. Just keep on updating. Does that make sense? The same stack frame. Keep on reusing it. And so deep down it kind of turns into a loop inside the compiler, but to us it's nice and pure and functional. All right. So if I tell G++ to compile with the fancy tail call optimization, I have to say that -o2, then it will work. It will not blow up the stack with a size 1 million vector. All right. That is weird, I know, to think about. Again, not testing you on this stuff. It's just very interesting to think about. Const all over the place, recursion to do looping. This is how it works. Okay. And then finally, there's an even easier way. C++ has already made it kind of a summing function for us. And so like functional programmers should just be calling functions all day long. Might as well use one that's in the library. So it's in the numeric library. And it's called accumulate. There it is, numeric. It's called accumulate, and you give it a range, an iterator, begin, end, and then you give it a starting value, and it accumulates into that accumulator. It turns into this code. So like here's some uses of it, and I might as well just show it to you. So I include numeric, and here's how you call it. So it's accumulate is the name of the function, and you give the thing you want to accumulate from where to where, from the beginning of v to the end of v, and then what do you want to start like accumulating into? The value 0, because you're adding. So that'll work as well. You don't even need the -o2, but they're all going to do the same thing. And honestly, this code is pretty much equivalent to the sum tail. Deep down, if you could see what the CPU was really doing, this code and this code is pretty much exactly the same. It's just as efficient. So you can get efficiency out of recursion if you use tail recursion. All right, that's the moral of this story, and functional programmers care a lot about that. All right, so I think that's what I wanted to show you for that. I do have just like a pre-made example that shows you some more functional ideas. There's some cool library stuff that is also in C++ that we can talk about. So remember that sum the squares from 1 to n problem that I gave you before? We can turn this into a functional problem. And I've already made the code. It's just like, it's already here. There it is. So you have your square function. We know what summing is. That's accumulate, right? So let me walk you through this code. We'll ask the user for the number that they want to sum up to, sum squares up to. So let's say that they type, I don't know, 5. Let's compile this. Sum squares fp. Like, it'll sum up all the squares from 1 squared to 2 squared, 3 squared, 4 squared, 5 squared. That's apparently 55, and I'm doing it twice in 2 different ways. So functionally, here's how we can think of this. Sum the squares from 1 to n. Like, how's the data flowing? You start with these numbers, 1, 2, 3, all the way to your n. Like, you need to create that range. There's a function that does that. It's called iota. It's a weird Greek, it's the name of a Greek letter. It has to do with something in math that creates a range. So, yeah, that will create a range for you. We can make a function that creates that range. And then there's a function in the algorithm library called transform that will take your range and mess with it and create a new range. 1, 4, because we're not mutating anything. 1, 4, 9, all the way to n squared. That's what we need next, right? And then, if we call accumulate on that new range of squares, that'll sum it up into a summed value. Do you see how that's how data could work? That's how it could all flow, and it would be happy? So that's what I'm doing here. So here I'm making a vector, and I'm creating a range out of it. All right. So technically, this is slightly cheating. It is technically making something with mutation, because it's making a blank vector of a certain size, and then it's filling it. But forget about that. It's still using functions. It's kind of cool. So that iota fills it with 1 through n, after I got n. And then transform is a function that takes like what you want to go through, this nums vector, like this 1 through n, the range, and then it also takes where you want to write back to. I'm going to be lazy and overwrite things. You could have been writing to a new vector though. And then you say what you want to do to every element. You give it a function. So it calls a function, calls square on each element, and it creates that. Does that kind of make sense? That's called transform. All right. So you can go look up all these. This one's in the algorithm library. There it is. It takes some things. Oh wait, just like this. Begin, end, where you want to write to the answer, and then a function call, a function to be calling. And there's some fun examples here. So like I want to call square. Like you give it the name of the function. You're passing a function to a function call. Isn't that cool? That's what you can do in functional programming. That's what it's really big on. All right, we just passed a function to a function. All right, that's the secret. So yeah, after you've done that, in your nums vector, now you have this range, the second range of squared values. We can use accumulate, we remember that one, to accumulate starting at 0, and there's our sum. Isn't that beautiful? I love it. The last thing I want to show you, the other way, there's one last way to make this even prettier and more functional. It's to use what's called a lambda expression. So a lambda expression in C++ creates for you an anonymous function, a function without a name. So we were using square just for this line, and it was kind of silly to have to make a square function that anybody could use if we only needed it once. So what we can do is pass along an anonymous function that does squaring for us. Here's the syntax for that. It's a function just in line that you can give that does squaring. So here's a function. You say brackets, then you say its argument, and then you give curly braces, and then you say what to do with the argument. What's the body of the function? This anonymous function. It's return x times x, right? X times x semicolon. You can put that in code. You can put that where it was in the transform. That's what a lambda is for. It creates a function on the fly without a name. It's anonymous. That will be called for you. So here's the same idea, like nums2 with iota to make the range. Transform, not with square, but you can just pass along the square function in line as a lambda. Isn't that cool? Like it's going to call this exact function, didn't even need a name, on all the values, and we're calling it nums2 now. Okay, and then accumulate keeps going, does the same thing. That's why you get the same answer. Isn't that neat? And so lambda is a huge deal. Like functions are a huge deal. And here's another way to make functions on the fly. If you just need one for one line. There's no use making one and polluting your namespace. Might as well just put it down here, and that's the one place you need it. Cool. So that's what I want to say there. And that is functional programming in a nutshell. There's plenty more to it. There's plenty of languages that are built just for functional programming. C++ makes it a little disgusting. Like this is not the most pretty of syntax I think you can imagine. It gets better in other languages that are built for this, but it is good to think about. It's fun to think about. There are pros and cons, so let's go through that. So imperative programming is the programming you learn in CSCI 40. It's all the stuff that I am testing you on. It's everything that isn't functional. Technically recursion is functional programming, so like that's important too. But mostly what we're learning in this class is imperative programming, and it's useful for a number of reasons. Like it deep down inside the CPU, it's doing imperative things. So if you want the power, like you can talk to the bare metal using imperative programming, using imperative code. Like you can overwrite variables inside the CPU. Like that's what's happening secretly deep down. And so you get more control because of that. Like there really is a state of the CPU. You can mess with that state. All right, you can mess with the memory. Memory really is changing. Functional programming is just meant to help you not make errors. Okay, there are plenty of cons to imperative programming that leads to different styles like functional. So you can get very complex code that's hard to maintain because you have to keep track of all the different ways that variables can change their values. All the state gets changed all over the place. That's hard to keep all in your head at once. So that's an issue with imperative programming. That makes it harder to debug, to reason about your code mathematically, prove that it's correct, or just even convince yourself that it's right. So for that, people have looked to other things. Functional programming is one of them. And so like some pros of functional programming like is usually that like you've just separated things into small chunks, and like it's easier to reason about each chunk because it's not going to mess with anything. All right, it's very small, concise, and it is not going to mutate anything. Because of that as well, it's easier to get some speed out of functional code. You can parallelize your code. You run it on like a big supercomputer that has a bunch of different CPUs. Because it's all your code is doing immutable things, it's not changing state. There's no state that needs to be synchronized. So you can just go hand off the problem, like whatever the answer is, your pure function will give it back. And a pure function is one that doesn't change any state. Okay? So that's easier to parallelize, which is useful for like graph GPUs and like games and stuff. That might be a reason to look into functional programming. And there are cons to functional programming too. I can imagine that you didn't really understand a lot of what I did today. That's okay. I didn't expect you to. It's much less intuitive, for sure. But if you understood anything at all, like pat yourself on the back. This is cool stuff. And it will help you to understand it. It's good to study. Another con, though, is it's not close to the bare metal. It's like you do have to copy things a lot if you want to keep everything immutable. And like that makes it easier to reason about, but you do waste some space because of that. And like the time it takes to do the copying as well. So there's a trade-off. There's always a trade-off. But functional programming is useful for certain situations in certain code. And it's a new tool in your arsenal that I encourage you to learn more about. So yeah, I think that's where I want to leave us today. Two completely different topics. Exceptions I'm for sure testing you on, but functional programming I am not. That was just for your benefit. Okay? So yeah, I think that's all that I have to say. Let me know if you have any questions, and I will see you in the next one.